All right, everyone. Um, so let's go ahead and get started for the lecture today. Basically, what I plan to do today is finish out this stiffness method for beams, and we'll start the stiffness method for frame problems, for which there are two handouts that I've just sent around. Before I do that, any questions on the homework that's due tomorrow, I think? And also, just hopefully you've all seen the mail. Dr. Liu is not available today, so I'll hold my office. I'll hold office hours instead in my office, 3 to 5. Nate?
How should we go about solving 1 and 2 by hand? They're unknown in both the additional matrices.
I'm not sure what you're asking. So, if I remember correctly, okay, yeah, so that's the cantilever beam with two separate I moments of inertia. And solving it by hand essentially means that you would have to go through the entire process, set up the element stiffness matrix for element 1, for element 2, assemble the global stiffness matrix, and then you would have a few different um, uh, a few different degree of freedoms that are free and they're specified. So I believe for the first problem there should be 4 degrees of freedom that are free, and for the second problem there should of course be 3. So I think, like I suggested last time, you don't have to crunch out all the numbers by hand. Let MATLAB do all that stuff. What I mainly want to make sure is that you understand how local element stiffness matrices are computed, how you're assembling them, how you would solve them by different boundary conditions. So I don't expect you to crunch out the numbers by calculator or something like that. Use MATLAB. MATLAB is already solving all of those things. Use the numbers from MATLAB. Show that by hand you understand the process if you were to do everything by hand. Make sense?
Yeah.
Okay. Any other question on the homework or anything else? Okay, all right. So let's jump into this topic of the distributed loads. Basically, the problem here is that, as you well know, for most beam problems, the types of problems that we have looked at until now are problems where the load is concentrated at some point. And if it's a point load, you can create a node at that point, and you can apply the load on the correct degree of freedom. But in order to be able to take account of situations where you might have a distributed load, there's no good way, at least in the stiffness method or in the MATLAB code, to specify that there is a distributed load from here to here in a beam problem. So the way we approach problems which have distributed loads, and it doesn't really matter whether it's a constant distributed load or some sort of a linear or some random distributed load, as long as you have a distributed load, the way that we approach this problem is by actually breaking it up into 2 subproblems. So what we'll do is on the particular span that we have this distributed load, we'll fix that particular span with fixed ends, right? So we'll assume that the ends of that span are fixed, and if we are given the distribution if we are given this distributed load, we can actually calculate reactions using the force method. Okay, so let me ask you this. So for this particular problem, if I have, instead of these rollers, if I have 2 fixed ends here, what is the degree of indeterminacy of that problem for a fixed beam? 3, right? Every if it's a cantilever beam, it's determinate. If you're adding another fixed end on the right, x direction reaction, y direction reaction, and the moment, all 3 are unknown. It's a degree of indeterminacy of 3. And if you're neglecting axial effects, then it's the degree of indeterminacy of 2. But even then, it's a reasonably indeterminate problem to solve for these reactions. So what we can solve for it. We can solve for those reactions using the force method. But instead of having to work from scratch, you can take a look at the take a look at this last page in your book. Let me see if I can pull that up. Not sure why it's not showing up. There we go. It's too bright. Okay. All right. So on this last page of your book, there is this table which says, maybe let me see if I can zoom in too. There's this table that says fixed end moments, right? So in this fixed end moments table, you have this many different loading cases of a span with either a point load, but both ends are fixed. If you keep scrolling down that table, there are different types of loads in this table. This is, for example, a uniformly distributed constant load with fixed ends at the two side. And what this table tells you is that the reaction or the moment at one end would be WL square by 12. Of course, symmetry means the other end would also be WL square by 12. If it's a different type of a distributed load, you have still different fixed end moments. And there are all these different cases for which you can read off the values from this table. Now, these fixed end moments allow us to simplify the problem and use these fixed end moments in our MATLAB calculation in a way that I will just show you. So keep in mind that for most standard types of loads, we have these fixed end moments already pre-calculated using the force method. If I asked you to calculate these fixed end moments using the force method, you could. Right? It's a 2 degree of indeterminacy, and if you work long enough, you would be able to calculate those fixed end moments. But since people have already calculated that, we can easily use it. So how do we take advantage of this for our stiffness method? Let's talk a little bit about that. The idea is that we'll break this original problem into two parts. One where we fix the span, so essentially anything outside the span is inactive, right? As soon as I say that this span is fixed, no matter what loading or essentially we've frozen the rest of the spans of this structure. And what we'll do is we'll calculate the fixed end moments, not calculate or read off those fixed end moments from those tables. And we will apply the equal and opposite moment to the problem that we can solve in MATLAB. So this part of the problem we'll solve by hand, which essentially involves reading off the values of that table. And the equal and opposite moment, fixed end moment and the reactions will apply to the actual structure. And if there's other loadings on the other spans, we include them here. We let MATLAB solve this problem. Then we take the MATLAB output and add this, our hand calculation to it. And as you can verify, if I add these two up, all of these fixed end moments and internal reactions will cancel off. Since the other parts of this structure are inactive, whatever response we get here would be actually the response of the original system. So that's the logic for dealing with problems that have distributed loads. We have to separate the problem into two parts, something that we have to deal with by hand, and the other MATLAB will solve for us. And we already know how MATLAB solves this, so I'm not going to go into too much detail about that, but I will tell you how to take care of this problem, for example. So let's take this example that's also on your handout. Cantilever, a fixed end at A, uniformly distributed load. There is roller supports in B and C, and there's a midpoint load at in BC. So the idea again here would be to break it up into two parts, where we will fix we will fix this guy. So this part of the problem is what we will solve by hand. And if I apply a uniformly distributed load to a problem that has fixed boundary conditions, I just told you I read off that value of WL square over 12 from that table. So I know that these two fixed end moments are WL square over 12. Right, I'll write that here, WL square over 12. And what would be the force? What would be these two reaction forces? Half and half. Half and half, right? So it's a symmetric. So just to take the total load, divide by 2. So WL over 2. Those would be the reaction forces. And for this particular problem, since the load is 2 kip per feet, length is 24 feet divided by 2, of course, that gives me 24 kips reaction at each end. So let me mark that. This is 24, this is 24. And the fixed end moment is 2 times 24 square divided by 12, which turns out to be 96 kip feet. And for this particular problem, I will convert everything to kips and inches. So, which is equal to 1152 kip inches. So this fixed end moment, that would be the reaction moment 1152. Those would be the reactions that I would get if I were to fix both those ends. Now I will take those fixed end moments and fixed end reactions and I will apply them as loads to my actual problem that I will send to MATLAB. So I'll apply the exact same 24 downwards, 1152 downwards, again 1152 downwards, 24 downwards. And this problem now, this is a problem that I can solve in MATLAB. I can create an input file for this problem, and as you hopefully are seeing right now, you can solve this problem. Another way to look at this problem is that you sort of replace that distributed load with the effect of that distributed load or an equivalent nodal force and an equivalent nodal moment is what this looks like. We have replaced that original distributed load with an equivalent force and moment that causes the same effect on this structure as this would have done. Make sense? So so let's see. This problem we have already just read off the values from the table, so there's nothing more to solve here really. This problem we can solve in MATLAB by creating an input file which should look like this. There are 4 nodes. There are 3 elements. So you can see that there's, I will maybe number those elements and nodes also. So I have node 1, node 2, node 3, and node 4. So since there are 4 nodes, what would be the size of the global stiffness matrix? 8 by 8. Each node has 2 degrees of freedom. And there's all these elements are also given in that input file. And I'm not sure if I have that input file on the handout. Doesn't look like I have the input file on the handout, but it's definitely posted on Blackboard as beam4.txt. So there are these 3 elements. Boundary conditions, it says node 1 is fixed both in the transverse displacement and the rotation. Node 2 and 4 are fixed in the transverse displacement. There's no boundary condition on node 3. Both transverse displacement and rotation are free. And finally, there are these nodal loads. So you can see that these nodal loads of minus 24, minus 1152, minus 24, minus or plus 1152 and minus 12, these are the nodal loads and moments that we have applied here. Note also that this moment is a negative moment. We're not talking about bending moment. We are talking about nodal moment. And if you just use the right hand rule, that moment on node 1 is indeed pointing into the plane that's negative. And whereas the other moment here is counterclockwise according to the right hand rule, that's positive, and all the three forces are pointing downwards, so they're all negative, which is what exactly that load is. So for a problem that has distributed loads, you would replace the distributed loads with their equivalent fixed end moments and reactions. Okay. And at that time, you can solve it as usual. Again, I'm not going to run through the code, but you can very easily check that the stiffness matrix for element 1 is this 4 cross 4. For elements 2 and 3, of course, it should be the same because E, I, and L, everything is same for those two elements from 2 to 3 and 3 to 4. So both of those give you this stiffness matrix. You know already how to assemble them. So I won't again go through that. And we have these degrees of freedom. Let me mark those. So I have degree of freedom, sorry, not horizontal, but vertical and rotational, that's 1 and 2. Vertical and rotational, that's 3 and 4. Same thing, 5 and 6 at node 3, and 7 and 8 at node 4. So clearly from this problem, 1 and 2 are fixed, 3 is fixed, and finally 7 is fixed. All the other degrees of freedom, which are 4, 5, 6, and 8, those are free degrees of freedom, for which you will again use that decomposition into free and specified parts and solve it. Hopefully you are experts at that by now. And and the idea would be that we would take these, we would solve this system, and we would add the fixed end moments from the original problem. This part we would have to do by hand. Okay, so this part we would have to do by hand, but we'll do that after we solve for this problem. So if you run through the MATLAB code, let me place a breakpoint at the solve line, and if I run it, open the beam 4 input file for this problem, it's already computed K global stiffness matrix 8 cross 8 double. By the way, double means double precision. When MATLAB says 8 cross 8 double, that double stands for double precision, which is essentially saying that MATLAB is storing up to 15 or 16 digits after the decimal point. So it has 15, 16 digits of precision after the decimal point. And this is important because when your problem sizes grow, this is a small problem, 8 cross 8, even though by hand it is very difficult to do. But in terms of computer problems, 8 cross 8 is a very small problem. When you are dealing with 800 cross 800 or even sometimes 8 million cross 8 million systems, it's extremely important to take care of this precision of each one of your entries. So that's why storing these values up to 15, 16 digits of accuracy is necessary, and sometimes even more if needed. So anyway, that's sort of the aside. And we have the global stiffness matrix. We have the force vector. You can see that that force vector already has read in the input file at the correct locations. And then we solve it. After we solve it, we have the correct displacements and rotations for one half of the problem. We solve for the reactions in line 54. which includes reaction forces and reaction moments. And after that point, it is all plotting. So I'll just allow it to run through. If I open up figure 1, that's the figure that's also given hopefully in your handout. Yep. So it shows you what reactions all of these are. And if this is hard to read, hopefully you all know how to zoom into that and actually find out the exact value of it. So it shows you deflected shape, reactions, and everything, which, and in the second figure, it also shows you shear force diagram in blue and bending moment diagram in red. And hopefully you all remember, for drawing the shear force diagram and the bending moment diagrams, we had to use the logic that we talked about last time, that you compute the local, you go to each element, calculate k times u of that local element, you will get the q and m forces and moments for that element, and you need to take mi and qj, the negative sign of that you have to take, so that you can draw the correct shear force and bending moment diagram. And that reminds me also that as Dr. Liu sent out an announcement in the code that we posted, that code, there was a plotting problem in that code. So even though it was computing everything correctly, it was not plotting the correct shear force diagram because there was a bug. It was assuming that all the elements have the same moment of inertia, but that has been corrected. The new plot beam 2D .m file has been uploaded. So if you don't have the latest version, make sure you download the latest version. And in that file, for problems that have varying moments of inertia along for different elements, it works for that as well. All right, so with all of this, what we are able to do is solve for the displacement, solve for the reactions. We get this deformed shape from MATLAB. And now we are back to trying to combine these two pictures. So as I mentioned, on the left half, this is the problem that we are solving by hand. We have fixed this end, and we are trying to add these two together. MATLAB has just found these reactions also for me: 25.5, 1296, 37.5, and 3. And we can check that. So hopefully you can make out these numbers, 25.5 and so on. So I'm going to use those reactions, and I'm going to sum up the nodal forces using those reactions. So 25.5 up, 24 down means a net of 1.5. There's a 1296 this way, 1152 this way, so that remains a 144 end moment in this direction. There's no moment, of course, at a roller, no external moment reaction at the roller. So whatever force or whatever external moment we applied remains as it is. There's 25 load down, 37.5 up. So that's the net 13.5. 12 and 3 are the other two forces. Okay. So all we did from this picture, this is the picture that we got from MATLAB. We've just recombined the applied loads and the applied loads and moments to find out equivalent nodal loads and moments, whether they are external forces or reactions. Okay. And we also have the deformed shape from MATLAB. What about this hand problem? What would be, I guess I've drawn the deformed shape, but the question really is, how do I combine the shear force diagram and bending moment diagram from what I got from MATLAB? And by the way, you can, I hope you can see that this is also the figure that we get from MATLAB. So this is shear force and bending moment diagram that we get for the second half of the problem in MATLAB. How do I, what would be the shear force and bending moment diagram for this part, the part that we have to do by hand? what would be, let's first of all say what would be the shear force diagram for this problem. Right? So we have 24 up, constant decrease by 2 kip per feet to minus 24 and then back up. So I'll draw that. So 24 up, 24 down, and a straight line connecting that. 24 minus 24 and 0 the rest of the way. So I have shear force diagram in blue. What would be the bending moment diagram for this? Right, it would be parabolic. We would start off with a positive or a negative? Negative moment of 1152 and end up at the same negative moment of 1152. So that would be something like start here and here, and it would be a parabolic bending moment diagram like this, 1152 minus 1152. And the equation for this can be easily calculated because we already know the end moments here. So minus 1152 plus 2x square over 2, and that would be this equation. Okay, so we have the shear force and bending moment diagram for the hand calculation part. We have the shear force and bending moment diagram from MATLAB. By the way, another interesting thing to note here is for MATLAB, all the bending moment diagrams would be straight lines in the span, right? Because everything here is a point load or moment. So anything that is curved because of the distributed load would occur in your hand calculation part. And at this point, all that you have to do is to really add them. I won't go through that. I'm sure you can visualize what the addition of these two diagrams would look like. And essentially what we get is a response to the original problem. Okay, so that's how we deal with distributed loads for beam problems. We break it up into two parts, and I'll break it up into two parts. One for hand calculation, where we freeze, we quote unquote freeze the span that has the distributed load, read off these values of the fixed end moments and reactions from the table on the last page of your book, apply those equal and opposite moments to the same structure and send it to MATLAB, and then recombine the hand calculation part with whatever output you get from MATLAB, and that's the solution of your problem. Make sense? Any particular questions on this? Okay, so hopefully that makes sense. And of course, if you have questions, you can post them on the discussion forum or come to my office hours. So let's switch gears a little bit and talk about the stiffness method for frame problems. So really the only difference between beam problems and frame problems is that when does a structure actually become a frame rather than a beam? Right. So if you have deformations that can potentially have bending, shear, axial, all of these things combined, and the orientation of the structure is not all in one direction, right? So, for example, this portal frame with an inclined roof, that's a frame structure where the underlying behavior of this system is a combination of both bending and axial deformations. And we will still be neglecting shear deformations because we assume that all the beam elements are thin beams, right? There will be shear forces, but there won't be any shear deformations. So let's see how we can deal with problems that have beam elements oriented in different directions, which essentially becomes a frame structure. So first of all, as usual, we will decompose the structure into nodes and elements. In this case, As I've marked, there are these 5 nodes, and each node in general can have degrees of freedom that are horizontal, vertical, and rotation. So there are 3 degrees of freedom per node now. Unlike the truss problem, unlike the beam problems where there were 2 degrees of freedom, we have 3 degrees of freedom now, which I will go ahead and mark here. 1, 2, 3. For 2, it would be 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, and the rotation is 15. So in general, the degrees of freedom that are associated with a node I, what would those be? If I have a node I, the degrees of freedom corresponding to that node I would be what? Go ahead.
3i, 3i minus 1, 3i minus 2.
Right. So for the truss problems and for the beam problems, it was 2i minus 1 and 2i. And maybe the easiest way to remember that is you just take the number of degrees of freedom per node. So for these problems, there are 3 degrees of freedom per node. If you have 5 nodes, then 5 times 3, total is 15 immediately, right? And so 3i would definitely be the 3rd degree of freedom associated with each node. The previous 2 would just be 3i minus 1 and 3i minus 2. So uh, um, which changes the MATLAB code a little bit, but not too much in comparison to the beam and the truss problems. So given that we have these degrees of freedom, our original problem or original idea of the stiffness method still remains exactly the same. We take a structure, divide it up into its nodes and elements, we assign the degrees of freedom to it, and then what we want is we want the force displacement relationships of individual elements. I have how many elements? For this problem, there are 4 elements. And for each one of those 4 elements, I want to know exactly how it behaves if I were to give it a displacement of, if I have 2 nodes, I and j in general, and maybe I'm talking about this structure right here. If I have 2 nodes, I and j, then I could give a displacement in the x prime direction at node I. I could give it a displacement in the y prime direction, or I could give a rotation in the z prime direction. Right? So each node has 3 degrees of freedom, and the question really becomes, how does this beam element behave if I were to give it a displacement in the x prime direction, y prime direction, or z prime direction? Same thing at the other 2 ends. So the total number of degrees of freedom associated with a frame element is what? Is 6, because 3 and 3, there are 6 degrees of freedom, 6 displacement and rotation degrees of freedom. And what is the corresponding number of internal forces and moments? 6, because there can be axial forces, shear forces, and moments, end moments or nodal moments at the two nodes. So what we want is to relate these 6 degrees of freedom for a beam or for a frame element with these 6 internal forces. But the good news is that we have already done all of the work that is related, that we need to come up with this relationship. Let me ask you this. I have a frame element oriented in some random direction, okay? In the local coordinate system of that frame, if I were to say that I apply or I want a displacement of delta I here, right? Then what would be the forces at the 2 ends? Would it be compression or tension? If I say the positive displacement of delta I in the x prime direction, compression, right? If I give a positive displacement here, it compresses by some amount. And have we done that sort of calculation? This is just a truss problem, right? In the axial mode, it is just behaving like a truss element. And similarly, if I were to give an axial displacement of delta J, again in the x prime direction, it's a truss element which I've extended, so that's a intention, which we already know is in the amount of AE over L times delta L. So in the axial direction, I already know from my beam theory, from my truss stiffness matrix, that if I have delta I x prime, delta I y prime, delta j x prime, delta j y prime, and the nodal forces qi x prime, qj x prime, and 0, 0, of course, because there cannot, for a truss element, you cannot have transverse forces. So we've already derived this long back with the truss elements. So the axial part is already done. And the other part of the good news is that the bending part is exactly like what we have done for the beam problems. So now if I ask you, if I have some beam element or frame element oriented in some direction, if I give it a displacement delta I y prime, then can you tell me what the forces and the moments would be at those two ends? We've done that calculation. That was case 1. Similarly, if I have a rotation here, that was case 2. Displacement at J, that was case 3. Rotation at J, that was case 4. So we've already done that calculation, but in the local coordinate system, right? Just like for the truss problems, we had local and global. Here again, we will have local and global coordinate system. We already know the relationship in the local coordinate system. The only thing is that we have to combine these two things. And by the way, first thing that you should note is the way I have written this relationship here, I'm saying QIY prime MI, QJY prime MJ. Because if you remember, for the beam elements, it was 4 cross 4. There was no axial component here anywhere. For frame problems, all we need to do is to add the axial component QIX prime from the truss relationship. So we'll go ahead and do that. All that it means is that I'll be adding AE over L here, minus AE over L here, minus AE over L here, AE over L here, and all the other entries in this are 0, because we are assuming that the axial response of a beam is not coupled or is not affected by the bending response of this beam. And let me ask you this. So let's consider this beam element in the horizontal direction. So global and local systems are exactly the same. Now, if I were to extend it by some amount, and after extending it, maybe take one of those ends, one of those nodes, say node I, down by some amount, while keeping everything else exactly the same, would the transverse force, these transverse force and moments required, would they depend upon the amount of extension that I've done? Right. So as long as extensions are small, they would not be. As long as the deformations are small, they would not be affected. They are essentially, we are decoupling the axial response of this frame element with the bending response of the frame element, which will not be true if it is what we call a large deformation problem, which we will not get into anyway. But this is something that you need to keep in mind. If I extend it by an appreciable amount and then try to move it down, I would need more forces. Why? Because there is some tension stiffening of this structure. So that's a second order, a higher order effect, which makes the problem nonlinear and more difficult to solve. But again, we will not get into that. Most problems in most civil engineering structures, we are able to solve with these small deformations where where the axial response and the bending response are decoupled. Okay, so that 6x6 system of equations is essentially the relationship that we are looking for frame elements. And once again, once this is done, this is the response in the local coordinate system. So this is the most important thing. Just like for truss elements, it was very important to make sure that we know which coordinate system are we working with. If in the local coordinate system for the truss element, this was the relationship. Again, in the local coordinate system for a frame element, this is the relationship that connects degrees of freedom at the two nodes, those are deltas and thetas at I and j, to forces and moments at I and j. Okay, so let me highlight that. This is local coordinate system. And just like the truss problem, this relationship is constant no matter what orientation of the frame element you have. Local coordinate system will always go along with that frame element, right? So local coordinate system will be always oriented along that along that frame element. So this relationship is essentially set in stone. You do not have to calculate it again. And but what we do need to do is what? Before, how would I use this local force element or force and displacement relationship for a frame element? Right. We would transform this, we would need to transform this to global before I can add it to a different frame element. So for example, I have this one frame element this way, another frame element this way. They both have their own local force and displacement relationships. I cannot add two vectors which are expressed in two different coordinate systems, right? If I have one vector here, one vector here in two different coordinate systems, I cannot directly add them. I would have to convert both of them to global, and then I can add them. Make sense? So that's exactly what we did for the truss problem. That's exactly what we are going to do for the frame problem. Just as a shorthand notation, I'm calling this entire 6x1 internal forces and moments with QM prime, which means M is the element, prime stands for the local coordinate system, Km is the element stiffness matrix, again in the local coordinate system, Dm prime is the degrees of freedom in the local coordinate system. So the question now is, how do I transform? And once again, the transformation is exactly the same as what we had for trusses. Why? Because transformation, really what we are doing is we are transforming vectors between one coordinate system to another coordinate system. It does not matter where that vector came from, whether it's a force or a displacement, whether it's a truss or a beam or what. A vector is a vector, and it will transform exactly the same way between two different coordinate systems. So we've already done all of that. We know how to go from x prime, y prime to x, y. Right? We know how to go between local and global using that transformation matrix. The only thing extra here is that we have this rotational degree of freedom. So since I've already written it, I won't ask you that question, but you should be able to see that for two coordinate systems, for both of these coordinate systems, in which way is the z direction pointing? In which way is the z direction, or z prime and z? They're coming out of the plane, right? So x cross with y, z is coming out of the plane. X prime cross with y prime, z prime is also coming out of the plane. Here, z prime and z both are identical coming out of the plane, right? So that means that whether you have a theta I degree of freedom or a theta I prime degree of freedom, they are exactly the same. So theta I, so that's the third relationship that we are going to need. And what that means is that in going between local to global, we previously had just these four values, cosine, minus sine, sine, and cosine. Though that 2 cross 2 was the transformation matrix. Now, if I want to go from Vx prime, Vy prime, theta prime to Vx, Vy, theta, all we need to have is that 1 in the third row and third column. And now the transformation matrix is 3 cross 3 instead of a 2 cross 2. That's the only difference. And just as before, the reverse relationship still holds. T transpose will take a global vector and give me a local vector. So if I want to convert local to global, then I pre-multiply with T. If I want to convert global back to local, I multiply with T transpose. And again, these two matrices, even the 3 cross 3 matrices, they are orthogonal. So T inverse is equal to T transpose. Okay. By the way, how many of you actually have taken a course in linear algebra? Is anybody missing that course? Because if I think I assume that everybody has taken linear algebra, but if you're not familiar with how matrices operate, then hopefully you've seen I've posted a few handouts. And once again, there is an appendix in that book in which basic matrix operations are given. I don't want to discuss all of that here. So make sure if you're not familiar, you go through that. That's basically the transformation that we would need. That's the transformation that is needed to convert the 3 degrees of freedom between local and global. Now, what we want really is to convert 6 degrees of freedom. But the good thing is that these 6 degrees of freedom are separated really. They are 3 for one node and 3 for another node. So just like for the truss problem, we can write a bigger transformation matrix that takes my 6 cross 1 vector from local to global. And of course, the off diagonal is just 0. And when I write this under tilde, that means it's a matrix. It's a matrix of what size? 3 cross 3 zeros. 3 cross 3 zeros here. This is a transformation matrix 3 cross 3 that was up here. And of course, it's the same transformation matrix to go between whether it's forces or displacements, right? They're both vectors. After that point, you already know the story. If we have the local coordinate system, we pre-multiply it with T. So T matrix times QM prime is equal to T matrix times Km prime, and I will also do T transpose times T and times dm prime. So hopefully you see the pattern here. This guy here is dm in the global coordinate system, right? If I take the local displacement or force vector pre-multiply with T, I get global. For the stiffness matrix, just like the truss problem, we have to do T times Km prime times T transpose. That becomes the K element stiffness matrix in the global coordinate system, which now involves 3 matrix multiplications of 6 cross 6. Absolutely nothing that you want to do by hand, right? So, and finally we have this QM, which is now this new relationship is the transformed relationship, taking the local coordinate system, expressing that same relationship in a global coordinate system. And you already know the story after this point. You take the global system, assemble the stiffness matrix, and solve for the degrees of freedom as usual. I'll talk about this in more detail, run you through the code also next time. But essentially, the same machinery that we have developed for trusses and beams works for frames as well. And I guess just as a closeout again, if you have questions, Dr. Liu is not holding office hours today. I will hold office hours from 3 to 5 in my office. Okay, so see you all on Monday, if not sooner, in the office hours.
Can I ask a question?
Sure.
Okay. So for this matrix,